Moving on with question number 9. A cylindrical cavity of diameter A exists inside a cylinder of diameter 2A as shown in the figure. Both the cylinder and the cavity are infinitely long. A uniform current density J flows along the length of the cylinder. If the magnitude of magnetic field at point P is given by n upon 12 AJ mu naught, find the value of n. So we have a cylindrical cavity of diameter A inside a bigger cylinder of diameter 2A. Now both the cylinder and the cavity extend infinitely long into the space.
Yes.
Right. And the whole cylinder carries a uniform current density of J along the entirety of its length. Now if the magnitude of the magnetic field at a point P is given, and we have to find out the value of n, right?
Yes.
So can you tell us how we'll solve this question today?
Yes. We do this by a principle of superposition, because otherwise we have no particular formula or insight into how to find the basically the magnetic field of a cylinder with a cavity.
Right.
But let's see how we go about it. So first we say there is a point P, and let's say this cylinder carries the current of uniform density J throughout.
Right.
Say in a particular direction, let's say into the plane of the paper.
Okay.
So it is carrying this current here like this. Now a cavity is there. So basically we have to find the magnetic field. So a cavity would imply that we can basically assume a cavity as a particular cylinder. There is a cylindrical cavity carrying the current in the opposite direction.
Can you explain us why we are taking this in this manner?
Yes, because see this, like let's say that this cavity is there.
Okay.
So if we assume this cavity, because the cavity contains no current, so the current carried is 0. Okay. So instead of saying that it carries a current 0, let's say that it carries a current of uniform density J both into the plane and both out of the plane. So basically the net current would be 0.
Okay.
But now let's separate this out. The part which carries the current into the plane we keep with this cylinder.
All right.
And the part which carries current out of the plane, we separated this out.
Okay.
So basically this is equivalent, or say electromagnetically equivalent to this one with a cavity.
Okay.
Now by the because the principle of superposition is valid, so the magnetic field created at this by this particular cylinder will be this and the sum of this carrying the current in the opposite direction would give us the magnetic field created by this hollow cylinder.
All right.
So basically we have the formula, or let's derive it again, that if a cylinder or wire carries a particular current density J,
right,
and we have to find the magnetic field at a distance r from center, so that would be B into 2 pi r equals mu naught I. So B into 2 pi r equals J into mu naught into the area,
right,
pi a square. We say a is the radius.
Okay.
So B equals J mu naught divided by 2r whole into a square.
Right. So we have the magnetic field, right?
Yeah.
Which is mu naught a square J upon 2r. Right.
So r is basically the distance from the center and a is the radius.
Okay, a is the radius here, right.
So for this case, we see basically the magnetic field will come out to be B equals J mu naught by 2 into the radius is a whole into the distance from the center is also A.
Could you just hold on there? You're solving this thing for the bigger cylinder or the inside cavity? This case that you're taking?
This I'm solving for the bigger cylinder.
Alright. So the radius is here, right?
Yes.
Okay.
So because the distance from the center is equal to the radius, so we can write down A and replace the A for R.
Right.
This gives us basically mu naught J A divided by 2.
Alright.
Okay. Now we consider this case.
A. Right.
This is a mu naught J A divided by 2.
Right.
Now considering this case,
The cavity.
with the cavity which we assume to carry current in the opposite direction,
Alright.
like this, into coming out of the plane of the paper.
Right.
See, this was from this center. This point P is at a distance of 3A by 2. Okay. And its radius is R is
A by 2.
A by 2.
Right.
So when we substitute for B, we get J mu naught by 2 into the radius would be A by 2.
Right.
Oh, sorry. Just a second. I made a mistake. Yeah, here this R is not the radius, it is basically the distance from the center.
Oh, okay.
So it will be a 3A by 2 here.
Right.
And here we put the radius. So it will be A by 2.
Right.
So this 2 cancels. We get J mu naught A by 6. A square
Okay. Yeah.
whole into 1 by 2. Because this was like A square, it was the radius square.
Right.
So we get basically by J mu naught A by 12.
Alright.
Now let's see that because this was in particular direction and this was in the opposite direction coming out of the plane, so the magnetic field because of this will be generated at P will be downwards, and because of this the magnetic field generated at P will be upwards.
Okay.
So the net magnetic field will be the difference of these,
Right.
so which will come out to be the difference of these two.
Alright. So could you please label this as B1 and B2 here? Right.
So say this was B1 and
Right.
this was a B2.
Okay.
So B1 minus B2 equals mu naught J by A 1 by 2 minus 1 by 12.
I'm sorry, but does A come in the denominator?
Oh, okay. It was mu naught J A by 2 and this is our A.
Right.
Mu naught J A by 2.
Right.
A comes in the numerator.
Yes.
So
That's correct.
it's basically mu naught J A whole into 5 by 12.
Alright.
So the value of n is 5.
Okay. So that was question number 9 for us, where we're given a infinitely long cylinder with a cavity inside, and we pass a uniform current density of J along its length. So the basic concept behind the solving of this problem is the principle of superposition, right?
Yes.
Okay, so we take a normal cylinder and we take the cavity as a separate cylinder with current being passed in the opposite direction.
Yes.
Or rather, because it's a cavity, we take it as like current being passed in both the directions.
Yeah.
And the one in which the current is in the same direction as the cylinder, we take it inside.
Yes.
And the one in which the current is being passed on the other direction, we take it outside.
And this, like, we are not creating a separate cylinder, we are just noting down the magnetic fields because of like all the current components, or all the current directions.
As a concept, it exists as a concept.
It's just a concept.
Right. So we superimpose the magnetic fields created by both of these, and we get the value of B1, which is mu naught Ga by 2. And on the account of this is for the cavity, right?
Yes, this is for the cavity.
Right. So B2 is a field created by the cavity, which is mu naught Ga by 12. And as a result of superposition B1 minus B2, we get the answer as mu naught Ga 5 by 12. And right. So mu naught Ga 5 by 12. And from the question n by 12 A J mu naught, solving this, equating, we get the value of n as 5, which is our final answer. So that's question number 9 for us. We'll start off with question number 10. An electron gun G fires electrons at the given velocity v, as shown in the figure below, and a uniform magnetic field B exists at an angle of 60 degrees to this. There is a point S in the direction such that GS is equal to 0.1 meter. Find the minimum value of B such that the electron hits S. Okay, so we have a new concept here wherein we are given an electron gun which fires electrons with the velocity v, and there it exists in a plane of a uniform magnetic field B at an angle of 60 degrees to it. So there is a point S which we have to take in the direction of B such that the distance from the gun to the point S is 0.1 meter or 10 centimeter. We have to find the minimum value of the magnetic field so that the electron can reach the point S, right?
Yes.
So can you tell us how do we go about solving this question?
Yes, for solving this question, basically we'll need to, in a way, visualize that how this electron will be going about, what the trajectory will be.
Right.
And using that, we'll be able to figure out as to why the minimum value of B is required and when it will reach S.
Okay.
So let's start and let's see that in this particular question, the velocity is not perpendicular to B. In fact, it is at an angle with B.
Right.
So for these type of questions, let's see the concept of how we divide the velocity into two components, one in the direction of V, one perpendicular to V, so that we can superimpose the motion.
Right.
And see what the motion actually looks like.
Ji haan.
So let's say we have this is a coordinate system.
Okay.
It would be actually easier to explain it through this.
Right.
This is X, this is Y, this is Z. So say along X there is a magnetic field B.
Right.
And at an angle of say 45 degrees, we have a velocity V and a positive charge particle is moving.
Right.
This is like the particle. Here we have an electron, it is negative, but the concept we are using is same.
Right.
So let's divide this velocity into two components, one in the direction of B and one perpendicular to the direction of V.
G.
So what we get is velocity V by root 2 in the direction of B, and another velocity here V by root 2, which will be perpendicular to B.
Right.
So see, this component which is perpendicular to B, this will be responsible for the circular motion or contributing to the radius. We had seen before that R equals mv by qb.
Right.
In this case, the radius will be m into v perpendicular divided by q into b.
Okay.
So this is v perpendicular basically. So v cross b, the force will go downwards, and if we, let's say we had just v by root 2 perpendicular to this and this did not exist, so the particle would be like sent from here and it would be doing a circular motion in the negative xz in the negative yz plane.
Right.
Okay, so the motion will be like this, but now we also have in the direction of b a velocity of v by root 2. So when we see from here, say we are seeing from here, the motion will be like this. It will be a helix,
Right.
and this will be constant.
Right.
Like the pitch of the helix will be constant because there is no acceleration. It is moving with v by root 2, and b cannot change the kinetic energy.
Right. Right.
So let's apply this principle to a question. First we find the kinetic energy. We have the kinetic energy of the electron. We can find its velocity.
Right.
That is quite simple. So basically half mv square equals 2 keV.
Can you explain the symbols over here? Like half mv square is equal to 2 keV. I mean, how did you arrive at that?
Yeah. We are given, say,
how did we get the kinetic energy of the electron as half mv square is equal to 2 keV here?
yeah, it's not given in the question, but basically we are just assuming it to be 2 keV.
Okay.
Which is kilo electron volts.
Okay. So if you're given this question in a JE paper, they'll be specifically mentioning this?
We'll be given the particular value.
Okay.
Here we have taken a value of 2 keV to just like numerically prove a point that we will get a particular answer.
Right. Right.
A particular minimum value of B.
Okay.
To arrive at. So basically we will be square root of 2 into kinetic energy divided by mass of the electron.
Right.
So by doing the particular calculations in the right unit, we will get velocity as 2.65 whole into 10 to the power 7 meters per second.
Right.
So
I'm sorry, what is this again?
Yeah, this is just the recap.
Okay.
Rearrangement of this particular formula. 2 keV was the kinetic energy.
Right.
So we've just put it here.
Okay. Right.
So we have a velocity now. Now let's see how the particle will move.
Okay.
So let's say this is a magnetic field.
Right.
In this direction. Okay, this is our B. Here is a point G, and here is a point S. Whole B is there.
All right.
And the particle was thrown at a angle of 60 degree with the B. This is the velocity of the particle.
Okay.
So we divide it, as we had seen, we divide it into the
two components.
This is 60
Right.
degree. We won't be mentioning the magnetic field here, we won't be drawing it, but
Right.
it is there.
Okay.
So this is G, this point is S, and so 60 degree, here it comes out to be V cos theta.
Right.
V cos 60, which is equal to V by 2, and the perpendicular comes out to be V sin 60
Root 3V by 2.
root 3 V by 2.
All right.
So this is an electron. We have a magnetic field here. So basically the force, we have to find the direction of force in which it will act. So this is the direction of B and V by 2 here. So this velocity won't change, or basically the direction of this velocity won't be changed.
Right.
But this component root 3 V by 2, because of this, see we have B, V cross B, and since it is a minus sign, so it will go into the plane of the paper.
Okay.
And viewing from here, if we see from here, the motion will be like a helix.
Okay. Right.
Just moving on. So we have seen the motion as a helix. Okay.
All right.
So basically we find the radius or the radius of curvature of this particular helix, what it will be. So the radius of curvature will be m into v perpendicular by qb.
Okay.
Now let's find omega. Omega is the angular velocity.
Okay.
Like it is rotating in a circle, so it will have some angular velocity.
Right.
Which will equal to v by r.
All right.
Which will be equal to, say, v divided by qb by m. This is the angular velocity. And say we have to find the time in which it completes one rotation.
Right.
So that will be 2 pi by omega. Omega is the angular velocity and 2 pi is the total angular distance.
Right.
That is because it completes the whole circle. T equals 2 pi by omega, which is equal to 2 pi m by qb.
Right.
So see, we have seen here that after a time 2 pi m by qb, it basically completes a whole circle, or basically it comes again to this particular line.
Okay.
So when it comes in this particular line, only then can it hit S.
Right.
Because otherwise it would be somewhere under the plane of the paper and won't be at S.
Right.
So basically we do the calculations now.
So basically it is a multiple of this particular unit of time, right?
Yeah, the time that has to be taken should be a multiple of this.
Right.
Now we find the pitch, or basically the distance between the two particular circles or loops of the helix. That is the pitch. So our pitch is equal to v cos theta, which was 60, whole into the time. Okay, because it is moving in the x direction the velocity is v cos theta, and we know the particular time that it will take. So this time is 2 pi m by qb, because once it completes a particular circle and reaches the same spot, that is the point, that is the time we have calculated.
Right.
Okay, so this comes out to be 2 pi m by qb whole into v cos theta, or yeah, we can write it v cos theta. Now here's the thing, that the time, or basically the pitch, the distance gs can be a multiple of pitch.
Right.
Okay, so this is the particular pitch, but gs can be equal to n times pitch.
All right.
Now let's equate. We know the value of gs, and using this we will find the basically the minimum value. As we see later why we can find the minimum value, not the maximum value.
Right.
Because maximum can be anything. We'll just see. So pitch equals, this is basically the pitch. This is equal to gs by n. We just swap b here, bring n there.
Right.
So b will come out to be n into 2 pi m. This is m to v cos theta divided by qb whole into gs. So see, this b comes out to be directly related to n. So if we are asked the maximum value of n, so that can be anything, that because the natural numbers extend till infinite.
Right.
But we can give the minimum value as n equal to 1. That is for just one pitch or just one circle completed. It reaches G from G to S.
I'm sorry, but there is one more b in the denominator here, is it?
Okay, sorry. That's a mistake.
Right.
Because b was supposed to go there.
Right. Okay.
So basically by doing the calculations for our particular case, we'll get the value as 4.73 into 10 to the power minus 3 Tesla.
Okay. So this is by replacing the numerical values for the given variables, right?
Yes.
All right. So that was question number 10 for us, where we had to find the minimum value of B such that the electron hits the point S. So can you just run through this again, like explain us the basic concepts in your
first we saw the concept that how the pitch how it moves in the helix. So
right.
For that there has to be a particular angle between the velocity and
so
B.
First we try to find the trajectory of the electron particle, right?
Yeah, exactly.
Okay, in the field and at an angle of 60 degree, right?
Yes.
Okay.
And then we note that because it is moving into the plane, so into this plane,
right?
So when it reaches here, basically the line of GS, only then can it strike S.
Okay.
And that happens whenever it completes a pitch.
Right.
So what we do is basically find the pitch and equate it equate it with GS in that case we get the minimum value of P.
Right. Okay, so that was question number 10 for us, and we get the final answer as 4.73 into 10 to the power of minus 3 Tesla.